Hello, thank you for your listening. The topic is discussing about the cooperative auto-regulation and its application. First, I want to appreciate ASI providing the chance to present my recent work. In nature, vast group of individual elements can cooperate and form highly complex global behavior through local interaction from multi-organism or complex animal structures such as schooling of fish and flocking of birds. This natural phenomena can be modeled as a multi-gene system. The multi-gene systems are self-organized systems consisting of many autonomous entities connected through local interaction. All the individual agents have a common objective leading to a collective behavior. Information has to be shared through the local interaction. Therefore, no agent has a global knowledge of the whole system, which means each agent can only access the signal of its neighbors. Multi-gene system also appears in various engineering applications such as distributed spacecraft and multiple UAV. The classical auto-regulation problem is to achieve asymptotic tracking and disturbance rejection for a class of reference inputs and disturbance while maintaining the stability of the closed-loop system by a feedback control. Give a leader system and a communication network and some followers. If the communication network have no constraint, which means each follower can freely access the signal of the leader. Clearly, we can use the classical auto-regulation approach to handle under this condition. This is the centralized control. However, there is some communication constraint always exists in the network. For example, the overall communication network consists of two groups. One group can access the leader's signal directly, the other one cannot. Under this condition, we can't use the classical approach to handle, but through the discrete control. The control objective is to design a discrete control law to achieve not only asymptotic tracking but also disturbance rejection in a class of multi-gene system. As the state of the leader system is not available for each follower in the network, we design the following mixed time and event triggered architecture to estimate the state of the leader system, where time-triggered observation is to estimate the state of the leader system, and an auxiliary observer with event-triggered communication is to reduce the information exchange among the followers. The main contributions are summarized as follows. Mixed time and event-triggered observers are proposed to estimate the state of the leader with discontinuous monitoring and localized event triggering. The interaction among sampling periods, topologies, reference signals, and related observability have been fully revealed, and not all non-pathological sampling periods are given. The mixed time and event-triggered architecture naturally excludes Zeno behavior. We now give an application to illustrate our design well. We consider the leader following formation control problem of multiple mobile robots, where leader and follower are moving in a following formation pattern with a constant speed. This vehicle is a leading robot. The formation performance is shown as follows. As we can see, all the robots move in the desired formation pattern as time going on. We now give concluding remarks to end the presentation. The problem of cooperative auto-regulation for heterogeneous linear multi-gene systems has been investigated by using mixed time and event-triggered observers. A distributed observer with time-triggered observations has been proposed to reconstruct the state of the leader, and an auxiliary observer with event-triggered communication has been designed to reduce the information exchange among followers. This is all my presentation. Thanks for your listening. Now let's go to the Q&A part.